In this video, we're going to discuss the divergence test for series. Given an arbitrary series from n equal 1 to infinity of a sub n, there are always two sequences that we can associate to that series. First, we have the sequence of partial sums, s sub k, where s sub k is simply the sum of the first k terms of our series. And secondly, we have the sequence of terms, a sub n. And so instead of adding all of the numbers together like we do for a series, we're just looking at the terms of the series as a sequence. If the series that we started with is known to converge, say, for example, to the number s, then we automatically know that the sequence of partial sums, s sub k, is going to converge to that same number s. This is the definition for what it means for a series to converge. This leads us to the natural question about what happens to the sequence of terms a sub n. In other words, what is the limit as n approaches infinity of a sub n when we have a series that converges? In order to answer this question, we're going to consider the nth partial sum for our series and use what we know about the limit of the partial sums to determine the limit of the terms. We start by considering the nth partial sum of our series s sub n, and we know that this is the sum of the first n terms of our series. And so we'll have a1 plus a2 plus a3 all the way down to a sub n minus 1 plus a sub n. So here we have the sum of the first n terms, s sub n. Now what we will observe is that if we exclude the very last term and we just look at a1 up through an minus 1 added together, this is s sub n minus 1. It's the n minus first partial sum. It's the sum of the first n minus 1 terms of our series. And so if I replace a1 plus up to an minus 1 with sn minus 1, we get the equation s sub n equals s sub n minus 1 plus a sub n. We can now subtract s sub n minus 1 to the other side of our equation because all three of these expressions here are just simply numbers. And so we get s sub n minus s sub n minus 1 will equal a sub n. And this equation allows us to write the nth term of our series as a difference of two partial sums. This is then helpful to allow us to compute the limit as n goes to infinity of a sub n, because now we can write this limit as the limit as n approaches infinity of s sub n minus s sub n minus 1. Here we have a limit of a difference, and using limit laws, we can write this as the difference of the limits. So we can have the limit as n approaches infinity of s sub n minus the limit as n approaches infinity of s sub n minus 1. Now comes our important observation about the limit of the sequence of partial sums. We're assuming here that our series converges, and in particular, we were assuming it converged to the number s. And so that means the limit as n approaches infinity of s sub n is going to equal s, and the limit as n approaches infinity of s sub n minus 1 will also equal to s. These are the exact same sequence of partial sums. We just are indexing by either n or n minus 1. But as n gets large, we move further along in our partial sum sequence in either case, getting closer and closer to s in each case. Regardless of what s minus s is equal to 0. This calculation answers the question that we posed earlier in the video about what happens to the sequence of terms of a convergent series. In this calculation, we've shown that the limit as n approaches infinity of the sequence of terms a sub n will always equal to 0 when the series that we started with converges. We've now verified the following fact. If a series from n equal 1 to infinity of a sub n converges, then the limit as n approaches infinity of the terms a sub n must equal 0. We can restate this fact in a logically equivalent way so that it turns into a test that will determine whether certain series diverge. For this reason, we call this restatement the divergence test for series. And this restatement states the following. It states that if the limit as n approaches infinity of our sequence of terms a sub n is not equal to 0, then the series from n equal 1 to infinity of a sub n must diverge. So if we had a series and we computed the limit of the sequence of terms and obtained a value that was not 0, say the sequence of terms converged to the number 5 or the number -3, or maybe the sequence of terms diverged to infinity or negative infinity, or even diverged completely, then this divergence test would tell us that the series we started with would automatically diverge. The divergence test comes with a very important caveat. The divergence test only applies if the limit of our sequence of terms is non-zero. If the limit of terms is equal to 0, the divergence test doesn't apply. As you can read in the statement, the test does not say anything about what will happen if the limit as n approaches infinity of a sub n equals 0. It only says what will happen if the limit of a sub n is not 0. And therefore, if we have a series where the limit of the terms is equal to 0, the divergence test cannot be applied, and nothing can be said in this particular case. It's possible that the series will diverge, but it's also possible that the series will converge. We would then need to use some other method to determine whether the given series converged or diverged. Let's take a look at a couple examples of series and see whether or not the divergence test applies to them. For our first example, let's consider the series from n equal 1 to infinity of n squared over 5n squared plus 4. In order to see whether the divergence test applies to the series or not, we need to compute the limit of the sequence of terms. In this case, that would be the limit as n approaches infinity of n squared over 5n squared plus 4. The sequence term here is a rational function in terms of n, and the largest power of n in the denominator is n squared. And so we can always compute this type of limit by multiplying and dividing by 1 over that largest power. So in this case, 1 over n squared divided by 1 over n squared. When we distribute this across both the numerator and denominator, we get the limit as n approaches infinity of 1 in the numerator, and in the denominator, we get 5 plus 4 over n squared. As we take the limit as n goes to infinity, the 4 over n squared will go to 0, and so our limit becomes 1/5, and 1/5 is not equal to 0. Since our sequence of terms for this series converges to 1/5, which is a non-zero value, this particular series is going to diverge by the divergence test. We don't need to calculate partial sums or anything else here. We automatically know that this series will diverge. For another example, let's consider the series from n equal 1 to infinity of n plus 1 over 3n squared plus 2. Again, in order to check whether the divergence test applies, we need to compute the limit as n approaches infinity of our series term n plus 1 over 3n squared plus 2. Again, we have a rational function here, and so we can multiply by 1 over the largest power of n in the denominator in both numerator and denominator, and so that will be 1 over n squared here. So when we distribute the 1 over n squared across both numerator and denominator, we're going to get 1 over n plus 1 over n squared in our numerator. And in the denominator, we're going to get 3 plus 2 over n squared. When we compute the limit, all of these terms with an n in the denominator, or n squared in the denominator, will have a limiting value of 0. And so here we have a limit of 0 over 3, which is equal to 0. And so here we have a situation where we have a series and the sequence of terms converges to 0. From this information, we can draw no conclusion. In this case, the divergence test does not apply. The divergence test only applies to series where the limit of the term is non-zero, in which case it says those series must diverge. In this case, the limit of the sequence of terms is equal to 0, and in such cases, the divergence test is inconclusive. And so we have no conclusion here. We have no idea whether this series converges or diverges based on the divergence test. If you'd like to try a similar example, you can pause the video and try to apply the divergence test to the series from n equal 1 to infinity of cosine of 1 over n minus 1, and the series from n equal 1 to infinity of 17n to the fourth over 8 plus n to the fourth. You can resume the video, and full solutions to both series will appear in a few seconds. When we take the limit as n approaches infinity of cosine of 1 over n minus 1, we see that this value approaches cosine of 0 minus 1, since 1 over n converges to 0. And since cosine of 0 is equal to 1, the limit of our term is 1 minus 1, or 0. Since we get a limit of 0, no conclusion can be drawn, since the divergence test only applies to series where the limit of the sequence of terms is non-zero. For our second series, we can multiply and divide the series term by 1 over n to the fourth and take the limit as n approaches infinity. And doing so gives us a limit of 17, which is certainly non-zero. And therefore, the divergence test applies to this series, and we can conclude that our series diverges.